Black band testing is an excellent technique that motor manufacturers use when adjusting new motor designs. It is not performed on every motor manufactured. It is performed on different designs. Black band is a systematic test procedure useful on large machines to indicate certain features of the machine's adjustment. And notably, those are the commutating field strength, main field pole and commutation pole air gaps, and even brush position. This information is obtained directly from curves known as black bands or buck boost curves. They're plotted from actual test observations. And the significance of these curves relates to the machine adjustments, differential between commutation, reactance voltage, and voltage induced by the inner. When performing the black band test, a low voltage generator called a buck boost generator is placed in parallel with the commutating field. And this allows us to put current in either direction that either aids or subtracts the current that's actually flowing in the commutating field. By purposely misadjusting the strength of this commutating field, we'll see visible arcing or sparking at the brushes, and that determines the limits of the spark-free commutation. Knowing the commutation limits under various load conditions allows us, the tester, to determine the permanent adjustments that must be made in the brush neutral and the commutating field strength. Adjustments are made like to the mag circuit is accomplished by exchanging or even adding magnetic steel and non-magnetic brass and aluminum shims behind the back of the commutating pole and between the motor frame and the commutating pole iron. First, the brushes are set to the electrical neutral position with the AC null method. The appropriate brush position is set before operating the motor. The first adjustment may use a static test of applying 120 volt AC current to the shunt fields and shifting the brush yoke to get the minimum AC millivolts between brushes. We always use a ground fault protector whenever we supply this AC current to our main field. We could use the AC curve method, and I believe it's even a more precise. Once precise electrical neutral is set, then we're going to set the neutral using the black band method. To set the neutral using that method, the machine is operated at rated armature volts with little current in the armature, and the buck boost current will be increased until slight arcing occurs. This data will be plotted on a graph that has a buck boost amps on the vertical axis and load amps on the horizontal axis. The load is a percentage of rated load. There should be equal margins on the buck and boost side for a well-adjusted machine. Now we're going to adjust the machine for loaded conditions. The motor is set to run at different load, such as 50, 100, and 150, and under each load, the buck current and the boost current is circulated in this loop. Under each load condition, the buck boost current is adjusted, so we initiate sparking and arcing under the brush, and then that value is recorded, and that data will be plotted on the buck boost curve. Ideal adjustment is for the black band to be wide and centered, as this example shows. If the load is outside the black band, the motor is going to arc. This ideal black band is wide and centered at all loads, indicating a well-adjusted machine. Black band follows brush position. In reversing machines, the entire black band tends to shift slightly to the boost side when running clockwise and to the buck side when running counterclockwise. In this example, the black band skews toward the boost side as load increases, which indicates weak interpoles. At the higher loads, there's not as much commutation margin on the buck side. And to correct that would require removing some non-magnetic shims behind the commutation poles and replacing them with magnetic shims. If the black band were sloped downward, the opposite action would be required. If a motor must run at strong and weak fields, the black band will slope upward to the boost side at higher loads with strong main field and downward to the buck side with weak main fields. So with the requirement for the motor to run in both directions and at base and top speeds, the common areas of the black band may look like this figure shown here, where the black band is narrowing over because the reversibility requirement and narrows at the higher loads because of the speed range requirement. So there's not much commutation margin at the higher load levels down here. Even filming that's developed on the commutator tends to drive the black band upward. So prior to filming, you may see this condition, and then after the brushes run a while and you start filming, you might be in this area of operation. Sometimes neutral may have to be adjusted so the machine does run black. Another consideration is motor shop power supply can be different than our facility drive equipment. While the mill uses DC drives that have SCR switching networks and there's transients involved and voltage output based on phase angle, the motor shop may use a column type variable transformer which has no switching. Black band is influenced by bidirectional rotation, operating in field weakening mode, interpole flux strength, main field flux strength, and neutral adjustment.